This is our video lesson number 3, circles. This is chapter 12, lesson 3, and we're in our textbook, and if you look at the title of lesson 3, it says Central Angles and Arcs. Not to be confused with arcs, which is what Noah was on, right? So we're talking arcs, parts of a circle. Okay, so this should be, I guess, Friday's work. So you spent Wednesday studying all about circles and radii, diameters and chords. And then Thursday, yesterday, you worked on tangents and did some exercises, all the while still reviewing the algebra for the AccuPlacer on Monday. So here we are on Friday, and now we're dealing with circles and central angles and arcs. So in your textbook, pages 497 through 499, 497, 98, and 99. So those 3 pages in your text. Don't have your text. Remember, I've scanned it in with the solution manual so you can work through the exercises and have all the solutions available too. Okay, so when you look at the lesson out of your text, you see there's a little bit about rainbows. And the first thing the author talks about is the parts of a circle. Now remember, the circle is the set of points equidistant from the center. Okay, so the circle is the entire black part. If we look at a portion of the circle, that is exactly half of it. I'm going to draw a diameter here. And then if we look at this blue section, that's called a semicircle. So semicircle. And I guess I probably should distinguish. It's not the diameter, right? The diameter is down here. Okay, so that goes through the center of the circle. Circle is in black. Here's the center of the circle. And the semicircle is this half of the circle, going from the end to the diameter, running around to the other end. So semicircle in blue. And of course, there's 2 semicircles in the picture. There's the one there, and of course, the one down here. Okay, so semicircle. Half of a circle. Okay, what happens if we have a circle and we don't quite have a semicircle? So let me scroll down here, another little sketch. Okay, so now let's consider, again, here's the center of the circle. This time I'm going to draw a chord that's not going through the center, so this is not a diameter. And we have now 2 parts of the circle. This part up here is called a minor arc, and the part on the arc, Joe, A-R-C, and the part on the bottom down here is called a major arc. So still has endpoints on the chord, but going around the long way, and this is the major arc. Major arc. Okay, so how do we talk about these things? Well, the endpoints are important. So as you note on the top of page 498, I'll use sort of the same idea there. If this is point A and this is point B, with the center of the circle being point O, we're using O for the center, then we can talk about the angle. So here's an angle here, AOB, angle AOB. That is going to be called a central angle. And we can talk about the arc. So this minor arc going from A to B is called minor arc AB. And we actually put a curvy piece on top. That's the minor arc. If we want to discuss the major arc going around the long way, okay, we can't use AB again. So if we simply have AB, we have a problem there because that's going to be our minor arc. So what we need is we need one additional point, and it could be any point on the arc down here. So we could say ACB. So going from A, traveling around, going through C, and arriving at B. So that's our major arc, ACB. And again, C can be any point on the arc here. So it doesn't have to be right there. Picture a point, but this point can be any point along this arc. So C could be over here. That's still major arc ACB. And the other thing your author notes is there's nothing magic about doing the letters in alphabetical order. You could have minor arc be A, and you could have major arc B, C, A. Okay, so the endpoint's always on the circle, and if it's 3 letters, that's going to be your major arc. And we also use 3 letters, by the way, for a semicircle. So if we wanted to talk about this semicircle, let's use different letters. Let's say X and Y. It doesn't do me any good to talk about arc XY because I don't know which one you want. Do you want the blue one or the black one? So for semicircles as well, you need to have a 3rd letter. So if this is Z, and now we talk about semicircle X, Z, Y, we know we're going around the blue end, okay, this way. So there's your semicircle going that way. But if we wanted the black one, we would need to have another letter down here. Let's say this is W. So now we have semicircle X, W, Y. And now I know I'm going around the bottom part here because I'm going through W. Okay, so the only arcs that have 2 letters are the minor arcs, right? 2 letters. And anything that has 3 letters will be a major arc or a semicircle. Okay, so there's your parts of the circle. Now, let's see how the angles tie into this. If you have a minor arc, and again, top of page 498 makes sense. So here's A, O, B. This angle, angle AOB, is called the central angle. And notice that A and B are on the circle. A and B are on the circle. And that angle is or has the same measure as minor arc AB. Okay, so you see the M for the measure. And if this angle happened to be, this looks about a 90-degree angle actually. I've sort of drawn it so that appears to be 90 degrees. Then we would say the measure of the minor arc is also 90 degrees. Okay, so the central angle and the minor arc have exactly the same measure, so that's sort of convenient. Now there's a new idea here that we can also talk about the major arc. So let's see, the major arc, that would be going around the other way. I need another letter, so let's pick C over here again. This will be the green one now, running all the way around. Okay, so this would be ACB, that's the major arc. And it too is going to be the same as an angle. Now, you know, what's the angle? Well, unfortunately, we have AOB again. But now we don't want the 90-degree angle. We want the, it's sort of a strange angle. We've never really defined this before. And if you look in your textbook, he sort of puts quotation marks there and say, we want this to be, you know, quote, the angle. And it's not really an angle according to the way we define these. So what we're going to do is we're going to call this a reflex angle, going all the way around, a reflex angle. Okay, and the degree measure would be 360 degrees minus the minor arc, so 270 degrees for that major arc. Okay, so the definition on the bottom of page 498 says the degree measure of an arc is the measure of its central angle. If it's a minor arc, you're going to be dealing with the regular angle that we're talking about, 90 degrees or whatever, some number here between 0, right, and 180 degrees. That's the way we define our angles, some number between 0 and 180 degrees. And if it's the major arc, then you're going to be doing the supplement of that, right? Actually, not the supplement. This is more than 180. This is 360 degrees minus the angle. So that's going to be our reflex angle. Reflex angle. Okay, and let's see, what else is in here? Now, you might want to read that a couple of times. When you work through the exercises, it's pretty clear how to talk about the measurement. I like the set 1 exercises, routes to Japan, you know, problems 1 through 7. So nice, quick, easy way to practice minor and major arcs, central angles. All right, okay, what else is in here? We have the arc addition postulate, which I think is sort of intuitive. Here's a circle, here's the center, and we have an arc, say A to B. So there's an arc, and then we have another arc going, say, from B to C. And we just note the arc addition postulate says that if C is on the arc, well, I guess to make this consistent with your textbook, here's B over here, and C is on the arc. Okay, so C is on arc AB, then we can add these together. So we're going to take AC, so the measure of AC plus the measure of CB is going to be equal to the measure of AB. So you have to think, you take this one, add up that one, it's going to be the same as the whole arc AB. So not too bad. Now, note that when he writes this in the book, he actually throws the letter C in there. He says the measure of arc ACB. But I have some questions there. You wouldn't do that unless arc ACB was a major arc, right? But we do want to just think that you can add these arcs together and they get the measure of the larger of the two. Why does it work? Well, remember we have angles here. So that angle there, we'll call that angle 1. That's the same as arc AC. There's another angle, angle 2, and that's the same as arc CB, 2 right here. And by the angle addition, you might want to go back in your text, the angle addition postulate said that if ray, in this picture, OC was between ray OA and ray OB, then we could actually add the angles up, right? Then angle AOC plus angle COB was the same as angle AOB. So the angle addition postulate from earlier in the course was adding angles. Now we have the arc addition postulate, which is based on the same idea. So arc addition postulate. We don't prove it, we just assume it to be true. Okay. The last thing, and I know this is a lot of material for this, so you might want to read it through a couple of times. The last bit here was a little bit on chords and their arcs. So we have a circle, we have a chord. Remember, a chord was a segment that has 2 points sitting on the circle. And let's just, for a number here, let's say this is equal to 6 meters. And I have another chord that's also 6 meters long. Let's see, that looks to be about the same. So let's say this was also 6 meters long. Then the theorem, 61, says equal chords have equal arcs. So if we put some letters here, let's say this is A and B and C and D. And the chords now, remember, are the segments. So if I said segment AB was the same as segment CD, then the theorem says the arcs have the same measure. So the measure of AB is the same as the measure of arc CD. And then the author just says, for simplicity, oftentimes we'll just call these equal arcs. So if the measures are the same, we'll just say AB is the same as CD. Okay, so that's theorem 61. Nice little proof there using congruent triangles. You can look at that. In fact, let's go ahead and do it real quick right here. I'll throw in 4 different radii. So this appears to be the center. There's a radius, there is a radius, there is a radius, and there is a radius, and we know that all radii are equal. Okay, so all those are the same. And by the assumption, we said that AB was equal to CD. I'll put 2 tick marks there. Right? And so if we look at these triangles, this black triangle has two sides and a third side. And if we look at the blue triangle, again, we've got these two sides that are the same and the third side. So the triangles are congruent by side, side, side. Let's go ahead and say that. Triangle using the black one, here's O. So triangle OAB is congruent to, and here's the blue one, triangle OCD, side, side, side. Right? So if the triangles are congruent, we know all the corresponding parts are congruent. So angle AOB, right? AOB is going to be equal to angle COD, right? COD, by corresponding parts of congruent triangles being equal. We know that. And so if we mark that in the picture, and I'll use green to do that, AOB is this one, and that's going to be congruent to COD, which is this one. These are both central angles. So if the angles are the same, then the arcs have got to be the same. That's what we said down here. Okay, angles the same, arcs the same. Okie dokie. And the last one is just sort of the converse of that. It just says that if you have equal arcs, then they have to have equal chords. So a circle has a couple of arcs that are the same length or the same measure. How about that? So A, B, there's an arc. Do it in red. Okay, and here's another arc that's exactly the same size. Okay, so CD again. And again, the sort of the hypothesis here is that AB is the same as CD, same size. Then we know that their chords have got to be the same as well. Okay, so the chord AB, the segment, is the same as the chord CD. And it sort of makes sense. I mean, you know, imagine if you would, instead of having CD like this, suppose you had a longer arc. So let's suppose we went all the way to there. No one, I think, would argue that the chord going from A to B is the same length as the chord going from C to D. They don't even look the same. So if the arcs are the same, the chords have got to be the same. If the arcs are different, the chords are going to be different. Okay. And that's it for lesson 3. I know that was a long video. How long we've been running? Wow, 17 minutes. Okay, so you might want to look at it a couple of times. Spend some time on the exercises. There's a nice bit on St. Peter's there on page 501. A little bit about concentric circles, night sky. By the way, the center of that night sky picture is Polaris, right? The North Star. At any rate, hope to see everybody on Monday for the Accuplacer test. Again, feel free to email me or message me or Mr. Melson for questions. Happy snow days.